Okay, so we're back here for part 2. Now, we're going to take the same basic question, but we're going to change it just a little bit here. So now, what we did on the first page was a chapter 8 review. We were talking about the confidence interval, which we use to estimate the true parameter, in this case, the proportion. Now, in question 2, Mr. Cavell claims that he is an 80% free throw shooter. Okay, so the claim is that this is the true parameter. This is the actual proportion of made free throws. The AP class watches him shoot free throws and believes that his true percent is lower. Thanks a lot. They take a random sample of 50 and he makes 32 of his 50 free throws. Is there convincing evidence at the alpha equals 0.05 significance level that his free throw percent is lower than 80%? Now, before we start writing this stuff down, back on the first page there, when we're doing the confidence intervals and we do state, plan, do, conclude, and I taught you instead, we can use the acronym PANIC, P-A-N-I-C. P is the true proportion. A is we're making the assumptions, those are the conditions, and then we also name what the interval was for the confidence. And then the I was we find the interval, and then the last part, the C, is where we make the conclusion. If we are doing a significance test, and this is what we are going to do here, a significance test for a proportion, it's going to be a different acronym. Now it's going to seem complicated, but again, each letter stands for something, and the acronym is phantoms, the word phantoms. The P and the H go together, the A and the N, the T and the O, the M and the S. Basically, this is what the book says as state is these two, and then plan is these two, and then do, and then conclude. And at the end of this, if you feel like you'd rather just think of it this way, that's fine. This is just to remind you of all the little things that have to get done in each step. So, P is we state the parameters. That's what the P is standing for. So what is, in this case, the true proportion? H, that is your hypothesis, your null, and your alternative. A is the assumptions. Those are the conditions. So we're talking about the random condition, 10%, large counts when we're talking about proportions. N is where we name the test. Okay, so what kind of test is it that we're doing? T is what we call the test statistic. So we're looking at T or Z for that. O is where we obtain the p-value, that is the probability. So we're going to get the test statistic. In this case, it's going to be a z-score. And with a z-score, we can then use normal CDF to find the probability of our value being that low or that high, whatever that is. So then we obtain the p-value. The last thing we do when we conclude is we make a decision whether to reject or fail to reject. And then lastly, we state the conclusion. So again, if you feel like this is just overcomplicating things, you state, you plan, you do, you conclude. Okay? I think this will be easier once you've done it a couple of times, just to remind yourself all the little pieces. So we're going to start with the statement. So let me put it like that. So we're going to start with the parameters. And in this case, we're going to say that P is the true proportion of free throws that Mr. Cavell makes. So P is the true proportion. Now, the starting point from this is the assumption that what he's saying is correct. he states that he is an 80% free throw shooter. So our null hypothesis is that P is equal to 0.8. Now you'll see this is what we call the null. This is P null. That value, the true proportion, is P null. You'll see why I write that in a few minutes. The alternative hypothesis, what the students believe is that he's not an 80% free throw shooter, that actually his percentage is lower than that. So the alternative, what we are trying to show, what we think is really the case, is that the true proportion is less than 0.8. So that is our alternative. That's what we would like to see, what we're trying to measure. If there's evidence to say that this is probably the case. Okay, so this is our pH. This is our pH from phantoms. We did the parameter, we did the hypotheses. The next part of this is AN. Now, A is the assumptions. So the assumptions, we have to look at the conditions. The first one, is it random? And the answer to that is yes. They tell us it is a random sample. Is it 10%? Does the 10% rule of independence work? Well, let's assume, or we are going to assume, that 50 free throws is less than or equal to 10% of his total number of free throws. So 10%, we will say yes. Now the last one is the large counts. Large counts, n times p, and then n times 1 minus p must be greater than or equal to 10. That's what we're going to test. Now in this case, the p-value, now this is important here. These are the true proportion. So we are going to use 0.8, 50 free throws times 0.8, and that gives us 40. N times 1 minus p, 50 times 0.2, is going to give us 10. Both of those are greater than or equal to 10. So yes, the large counts works, which means we can say that our distribution is approximately normal. Okay, that's really important that we're able to say that. Now you might say, whoa, 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 Mr. Cavell, his sample proportion was 32 out of 50. The sample proportion, p hat, was 32 out of 50, which is 0.64. Why are we not using that? Well, because everything that we're doing is to measure against the true proportion. So we start, again, with the assumption that this is the case. So this is why we're going to use this when we do the large counts condition for that, for normality. Okay? Now, the name of the test, these are the assumptions. The name of the test, we are doing what is called a one-sample z-test. One-sample z-test for the proportion p. One-sample z-test. Now, when we start talking about means, this could be a one-sample t-test for that. Okay, so we've got pH, AN. Now the next part is where we need to test the statistic, and then we need to obtain, TO, test the statistic and obtain a p-value. Now for that, we're going to do this by hand, but then I'm going to show you on the calculator. On your formula sheet, the standardized for inferential statistics, we're doing inference here because we're trying to make conclusions based on our data. The standardized test statistic is the statistic minus the parameter divided by the standard deviation of the statistic. Okay, so first of all, I'm going to write this down. And I know this is kind of a mess. The standardized test statistic is equal to the statistic minus the parameter, there's a lot of vocabulary here, divided by the standard deviation of the statistic. Okay, now this is what's on your formula sheet. And you might say to yourself, that doesn't seem very helpful to me. But we have been doing this since chapter 1. Back in chapter 1, we had a simpler way of writing this. We said, this is the formula for how we calculate a z-score. Is we take the value that we're testing, we subtract the mean, and we divide it by the standard deviation. And what that gives us is a z-score. Well, that is exactly what we're doing here. Now we're taking the statistic, that is our p hat. Okay, so I'm gonna write this now. The standard test statistic, the standardized test statistic is z equals the statistic, that is our sample proportion. That's where we're gonna use it. Minus what we claim is the true proportion, what Mr. Cavell claims is the true proportion, that's the parameter, divided by the standard deviation of the statistic. Now, we don't know the real standard deviation, so we have an expression for that. It is the square root of p hat, square root, hold on, of p naught times 1 minus p naught divided by n. Okay, now where is p naught coming from? That's this. That is the true proportion. Because again, we are measuring this based on the true proportion. All right, so we've got the p hat, the sample proportion, minus the parameter. The standard deviation of the statistic is we are using the 0.8 to do this. Okay, so we're going to substitute values. Now we said that p hat, off on the side here, was 32 out of 50. As a decimal, that is 0.64. Z equals 0.64 minus the true proportion, according to Mr. Cavell, is 0.8 divided by the square root of 0.64. Nope, sorry, 0.8. 0.8, not the sample proportion, the claim proportion in the null, times 1 minus 0.8, or you could say 0.2 divided by 50. Okay, now we're going to work this out. I'm going to do the square root part first. 0.8, that's 0.2 divided by 50. And that's equal to 0.0566. 0.0566. And if I subtract 0.64 minus 0.8, that is negative 0.16. Now, this right here is the standard deviation of the statistic. Okay, this will come up again in a little bit. If we divide, so if we do negative 0.16 divided by 0.0566, we get negative 2.827. Negative 2.827. Negative 2.827. This is our z-score. This is our standardized test statistic. Okay, so in terms of phantoms, here we just found the test statistic, but that is not the p-value. But we can use this to obtain the p-value. Now, first of all, you notice this is negative. Well, that should make sense because if you think of this kind of like when we're doing a normal distribution, if this value is smaller than what we think the true proportion is, we will be to the left of that. If I draw a normal distribution curve here, if I'm saying that the mean is 0, that the proportion is 0, here's standard deviations. 1 standard deviation, positive 1, 2, and 3. Minus 1 standard deviation to the left, minus 2, minus 3. Notice we are very far off to the left here. That minus 2.827 is way over here. So what is the probability that our value is this low or lower? That's what we're looking at here. What is this? That is going to be our p-value. Now you can use a z-score table since we actually found the z-score, but you could also just say, hey, let's use normal CDF. Our lower bound, I'm going to say, is negative 1,000. The upper bound is negative 2.827, where the mean is 0 and the standard deviation is 1. So if I go through that and we do normal CDF, negative 1,000, I've already typed it in here, negative 2.82701, calculate 0.0023. Very low probability is 0.0023. Now you might be thinking though on the normal curve, well, what if I had used Mr. Cavell's claimed proportion of 0.8? Would I have been able to still do this? And if we had done it that way, if I said, okay, normal CDF, if we went from negative 1,000 to 0.64, where the mean is 0.8, but the standard deviation of the statistic was 0.0566 or 0.0566. Let's see, that should give us the same thing. I'm curious here. So negative 1,000. So this time I would use the sample proportion where the mean would be 0.8 and this would be 0.0566. Oh, let's see what happens. Come on, come on. Look at that. Woo, 0.0023 or 0.0024. So that would give us the same thing. Personally, I would go with this. I think it's a little bit easier and less things that you have to change, but this will also give you the same thing. All right, now that is the end of part 2.